Hello students, welcome back. Today we will continue with lecture number 6 of chapter 9 Ray Optics and Optical Instruments. I hope you had watched my first 5 video lectures of this chapter. If you like my video if you like my videos, then please subscribe this channel. Okay, now we have already started with refraction. We have studied about refraction, Snell's law, refractive index. Okay, now today we are going with one more important topic, right? Apparent height, real height, apparent depth, real depth. Okay, now you might have observed whenever you are observing anything in water, right? You will observe that the height that you are observing is different from the real one. Just for example, if you are observing an empty swimming pool, okay, then the height you observe is the real height. But when this swimming pool is filled with water, okay, you will not find it as deep as it was seen earlier without water. That means the depth of swimming pool appears to be lesser when water is filled in it, right? You might have also observed that if you are just putting a spoon in a glass filled with water, you might have observed that it's not straight, it's broken at the interface. It appears like this, right? So whenever the medium changes, okay, it appears different. So whenever I will use the word apparent height mean or apparent depth, that is the observed height or observed depth when there is some other medium. Okay, and the other word is real height and real depth. Okay, now let's see. Let's take this with water. Okay, now there is an object. Let's take an object place here. O, this point O. Okay, now when the rays of light, okay, when it's going in this way, at this interface, this is the normal. Okay, what will happen? Here it is water. So let's take the refractive index N2 and this as N1 air or vacuum. So what will happen? Here I feel water. So water is optically denser compared to air. So what will happen? The ray will bend away from normal, right? So it will bend in this way. Now if there is a person who is observing from here, right? The object will not be observed here. It will not be observed at that point when I am extending this ray. This will be the image. The observer will observe the image at this place, right? So if this is the depth, if this is the depth, this is original height HO, right? Or original depth, I will say. Then when water is present, the depth appears to be only this much. Let's take HI. I'm using I for image, height of object, height of image. Okay. Now, why does this happen? Right? Our eyes, okay, they perceive the light in a straight line. Right? Our eyes perceives or assumes that light travels in a straight line. So when the observer observes here, okay, it is assumed it perceived as a straight line. So when it is extended, the object placed here will be appeared at that place. Clear? So I can write it down this as angle of incident. Clear? So this will be also theta 1. Okay. Now this will be angle of refraction, theta 2. Clear? See this alternate angle, you can see here, these two parallel. So these are alternate angle same. This theta 2, so this will be also theta 2, vertical opposite angle. Okay, sorry, this will not be theta 2. This will be theta 2. Okay, this angle complete will be theta 2. So this is again Z position. So this will be also theta 2. So this is theta 2, vertical opposite this theta 2, and this alternate angle theta 2. Clear? Okay, so what I can do, I can just mark the name this as point P. Let's take P I and this point Q. Okay, now see these two triangles. I'm separating these two triangles. First, this triangle P I Q and this triangle POQ. This is theta 2, this is theta 1. Okay, now what is point Q? Here, point Q, that is point of incidence. At this point, this ray is incident. So I can write it down according to Snell's law. It's n1 sine theta 1 equal to n2 sine theta 2. But see here, where it is n1, the angle is theta 2. So it will be n1 sine theta 2, n2 sine theta 1. The refractive index we have taken this as n2 and this as n1. Okay, so it will be slight, there will be slight change. Now when theta tends to 0, sine theta equal to theta equal to tan theta, right? So assuming that this angle is very small, what will happen? N1 tan theta 1 equal to N2 tan theta 2. Okay, now tan theta 1 from this triangle opposite PQ upon PO, that is HO, and tan theta 2 from this opposite PQ upon adjacent PI, that is HI. So using this triangle I found out tan theta 1 and tan theta 2. So N1, what is tan theta 1? PQ upon HO. Sorry, my mistake. It's theta 2 here and theta 1 here. So it's PQ upon HI equal to N2. And what is theta 1? PQ upon HO. So PQ gets cancelled. So what does our formula says? And HI by HO, height of image upon height of object. What is HI? Apparent height means the height observed. And what is HO? Real height. So what will be this? HI, it goes on this side. It's N1 by N2. Okay. What is N1? Refractive index of rarer medium. And what is N2? Refractive index of denser medium. Okay. So whenever the observer observes from rarer medium and is observing the object present in a denser medium, remember it's optically rarer and optically denser medium. Okay, it's not rarer, it's optically rarer medium, optically denser medium. Okay, then the height of image to the height of object, the ratio will be equal to refractive index of rarer medium, optically rarer, to refractive index of optically denser medium. Or else we can simplify in this way, height of image upon height of object. That will be equal to refractive index What is N1 here? Observer of observer's medium upon refractive index of object's medium. Clear? Remember this height of image to height of object. In numerator, you have to take observer's medium, and in denominator, you have to take object's medium. It can be interchanged. Clear? Just for example, we can take that if there is a fish, okay, and the fish is observing a point here, okay, this is the point. Clear? This will be the real height, right? So what will happen? This will be normal. From here away, this will be reflected towards normal because this is rarer, this is denser, and one and two. So where this object will be appeared to the fish, okay, however our eyes takes, it takes light as a traveling a straight line. So this way. So this will be the height of object, right? So in that case, hi by h0 will take same, but n1 observer medium will take n2. Okay, in this case, hi by ho will be equal to n2 by n1. Okay, so remember this. In numerator, you have to take observer's medium refractive index, and denominator, you have to take object's medium refractive index. And that's for hi by ho, ratio of apparent height to real height. Okay, same way for depth also. Clear? So I'm repeating this apparent height and real height. What happens if there are any object at this place? Let's say this is the depth HO, right? So when an observer is observing from outside, this depth is appeared to be raised at this level, right? So first we draw the diagram. We have separated these two triangles. Clear? Now what is Q? This is the Q, the point of incident, okay, at the interface. Clear? So according to Snell's law, n1 sine theta 2. Why theta 2? Because n1 the angle is theta 2, n2 the angle is theta 1. So when n1 sin theta 2 equal to n2 sin theta 1. When theta tends to 0, sin theta equal to tan theta. So replace here with tan theta. Here, put the value of tan theta and then finally find out this formula. And remember, for MCQs, okay, or objective question, whenever the observer's medium and object medium are different, or whenever an observer is observing from one medium to another medium, then the height or size of the object appears or will be having the height or size totally different from its original size. So the height of image to height of object will be the ratio of refractive index of observer's medium to refractive index of object's medium. Clear? So just go through this and note down this topic. Okay, now let's take one example. Okay, let's take an example that let's say there is a pole. Okay, there is a pole whose height is, let's take 5 meters. Okay, and a fish is observing that pole. The refractive index of water is 1.33 and refractive index of air is 1. Clear? Now this is the real height, so I will write down HO. Now you have to find out the height experienced by the fish in water. Clear? So what was our formula? HI upon HO was refractive index of object observer's medium. Where is observer? Here. So N2. Two objects medium. Where is the object? Outside. N1. So this will be 1.33 upon 1. So height of image will be 1.33 into HO, 1.33 into 5. Okay, it will be equal to 6.65 meter. Okay, so the height of the pole experienced by the fish is higher compared to its original height. So from this, remember that whenever an observer is observing from denser medium to rarer medium, means the observer is in denser medium and the object is in rarer medium, the height or the size experienced is always higher than the original size. And in reverse, if the observer is in rarer medium and the object is in denser medium, then the height experienced is lesser compared to the original height. Clear? Just note down this example. Okay, now we will take one more interesting case. Okay, I'm explaining you one more interesting case. Earth. Okay, let's take this as Earth. Okay, now Earth is surrounded by atmosphere. Okay, this is the atmosphere. Now you might have studied in standard and about atmospheric refraction also. Okay, now see, you will observe that. Now you have to think that whenever we go at higher altitude, okay, the medium becomes optically rarer. Yeah, and that is the reason at high altitude the pressure is less. Okay, on the surface of the earth the pressure is higher compared to higher altitude, right? And that is the reason people feel difficult in breathing. Clear? Because the air there is not as denser as it is on the surface of the earth. So, same way, at higher altitude, the medium is optically rarer. Clear? Compare and at lower altitude, the medium is optically denser. If I take this as the horizon, okay. If I take at this as the horizon, and if sun is present at here and far away, okay. At this point, this is the horizon. So, okay, the person standing at this point would not be able to visualize the sun. Okay, but see what happens. What happens? See, let's take this as a height. Okay, when a ray of light is coming in this way, okay, at this point, this is the angle of incident. Now, the air above is having rarer and below is having denser medium. So, what will happen? It will bend towards normal. So, it will be bending towards normal. At this point, again, this portion is denser compared to this, so towards normal. So, what happened? It will not be in a straight line, right? In reality, this will be a curve bending towards normal. So what happened? A person, the sun, the rays coming at this way in a straight line, when it enters the atmosphere, when it enters the atmosphere, when it moves ahead, it is continuously entering from rarer to denser. So it will bend towards normal. This light will bend. Okay, clear? And when I will draw a straight line, if we, our eyes considered light as a straight line, okay, perceived as straight line. So sun will be appeared at this position. This is the real position of sun. This is the apparent position of sun. Okay, this angle is approximately half degree, right? So, due to this, okay, the sun is seen in the morning before its actual rise. Okay, sun is seen 2 minutes earlier, and in the evening time, it is when the sun sets, even after that 2 minutes, it is seen. So in standard 10, you might have studied this question that the apparent length is 4 minutes higher of a day. The apparent length of day is 4 minutes higher than the real length of the day. 2 minutes early in the morning and 2 minutes late in the evening. Clear? So this is due to the refraction, atmospheric refraction, I would say. Okay, as we move ahead, it is entering in denser and denser medium. It will bend towards normal, 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 and this the sun is appeared at this way. Clear? So this was about one more interesting case. Okay, so student, that's it for today. In our next video lecture, we will start with total internal reflection. Okay, so for today, that's it. Thank you.